Hello, welcome to this CNIT Conversation entitled Machine Learning at the Edge of the Network. It's a conversation that I'm sharing with my colleague, Professor Carla Fabiana Chiasserini from Politecnico di Torino. My name is Sergio Barbarossa from Sapienza University of Rome. So what we want to talk about today is the synergism that we can create by merging machine learning algorithms and 5G networks and beyond. So a brief summary. First of all, we will try to motivate why machine learning and network can benefit from each other. And then we will focus on a good place for them to meet, which is the edge of the network. We will show application motivating this merge. And then I will list some challenges arising from the merge and highlight some possible future directions. And then I will leave the spot to my colleague Carla, who will talk about federated learning and the fundamental trade-off between decision quality, service delay, and energy consumption achievable at the edge of the network. So, first of all, we really believe that machine learning and 5G networks can really benefit from each other. In particular, networks need machine learning to become more autonomous with respect to today and learn how to optimize the allocation of network resources, whereby resources, I mean not only communication resources, but also computation and storage. And on the other side, machine learning needs networks to be able to deploy really pervasive applications, in particular all those applications that are delay sensitive, energy efficient, and context aware. An example of them comes from this joint European and Taiwanese project called the 5G CONI, in which I'm involved. 5G CONI stands for 5G Private Networks for Connected Industries. And this is a typical case where we really need to implement intelligent machine learning mechanisms at the edge of the network to provide an efficient control of the manufacturing process. And then here I list some potential applications where the merge between learning and networks can be really useful. So on the left side, we see cases where machine learning can help networks to become more efficient. And if we have in mind the protocol stack in typical networks, we go from the physical layer, where machine learning can be useful to tackle, for example, the pilot contamination problem, which is one of the problems that is preventing a really dense deployment of radio access points that we know it's an essential strategy to make 5G networks to become more energy efficient. By the same token, machine learning can be useful to mitigate the intercell interference, which is again associated with the dense deployment of radio access points. If we go up on the protocol stack, machine learning is also useful for devising network routing mechanisms and also to extract analytics from the data running on the networks. And these analytics can be used, for example, to implement a proactive strategy as opposed to reactive. And we know that to be able to be proactive, we need accurate prediction mechanisms, which can be provided by machine learning algorithms. On the other side, the networks are fundamental to enable a really pervasive introduction of artificial intelligence in our everyday life. Typical examples, one is Industry 4.0 that I mentioned before, but we also have digital twins, autonomous driving, the management of smart cities, virtual augmented reality, navigation of unmanned aerial vehicles, especially fleet of them, and so on. Just to mention an application taken from the same projects that I mentioned before. So this is an example where we have a manufacturing premise in Taiwan. And here we have 5 machines. And then our colleagues created a 3D model of each machine. And then based on these models, in the project, we built some applications running over an HoloLens and another one for a virtual reality application. And these applications enable a remote controller to really control what's going on in the manufacturing process. And for example, in the virtual reality case, it's fundamental to have a very high data rate link from the, for example, for the HoloLens, from the HoloLens to the remote expert. But at the same time, we also need ultra reliable and no latency communications as offered by 5G to be able to take measurements from the sensors and then run a machine learning algorithm to understand what's going on and send the commands back to the machine. Going into the specific, for example, this merge between 5G and machine learning enables intelligent testing so that a cloud controller can send a series of motion commands to a particular moving axis, for example, to reduce vibration. And also in this case, what is fundamental is to really take advantage of the ultra reliable and low latency communication made possible by 5G. Now, as in many engineering cases, nothing typically comes for free, so there's no free lunch, essentially. So when we introduce this machine learning mechanism to our networks, there are also a series of challenges that we need to be aware of and to be able to tackle them properly. So I'm listing here some of them. First one is probably the fragility against adversarial attacks. And this is something that cannot happen to humans, but it can happen to deep neural networks, for example. Then the second one is explainability. Nowadays, even though deep neural networks are very powerful and useful in a variety of applications, but still there is no rigorous theory foundations explaining why the neural network takes some decision based on the training phase that it has been going through. And we are also observing a sort of law of diminishing return from deep neural networks, which raises a question of sustainability of this mechanism. So how long is this approach followed by the mainstream machine learning field is going to be sustainable in the future? Now, possible future directions. One of them is goal-oriented communications, where we take the scope of the network into account in designing the communication mechanism. And we need to be able to learn in the presence of uncertainties, as typical. And possibly we can move on by merging the typical the data-driven approach that is typically followed in the machine learning community with model-based approaches and so on. And at this point, I will leave the spot to my colleague Carla from Turin. Please, Carla.
Thank you, Sergio. Hello, everyone. So I'm going to focus on one of the aspects that Sergio mentioned, that is distributed learning, which offers very interesting challenges and also big opportunities. And in order to do that, let me refer to one of the most prominent application scenarios, that is the automotive scenario, which indeed requires ultra low latency guarantees. So it is easy to see that in this case, machine learning is extremely important. Automated cars are already a reality, and we will soon have autonomous vehicles, starting with applications such as platooning. So in this scenario, vehicles, as well as what we say the so-called smart city, will have to collect a huge amount of data and then use this data to understand what to do. That means which actions should be taken. So while collecting data may be relatively easy thanks to the variety of sensors with which vehicles are and will ever be equipped, making decisions requires to process this data and learn which decision is the best one given the current situation. And here is where ML, machine learning, comes into play. So in particular, the learning process or training of a machine learning model requires data as well as computing and memory resources. Once the machine learning model has learned, then it can be used to make decisions on the spot online. This is called inference. An inference phase requires not much data, but some memory and computing resources. However, inference is a much lighter process than training. So the interesting story in our case is indeed learning. Now, traditionally, machine learning models have been trained in a centralized manner, that is, using a single computing node. However, there are some machine learning tasks that require lots of data, computing resources, memory, and there are some machine learning models that are so complex that their training has the same carbon footprint as that of an average car during all its lifetime. So more recently, Google has proposed a distributed paradigm called Federated Learning, according to which several nodes cooperate in order to learn and produce a machine learning model that can make good decisions while preserving data privacy, which is a big plus. So here is a simple representation of the federated learning paradigm. We have a coordinator that we can think of as a node in the edge of the cellular network, perhaps close to the base station, since we have to keep the latency low. And then other nodes devices that act as learners. The learners receive the model to train from the coordinator, train the model locally using their own data and resources, and then return the output to the coordinator, which leverage these models, averages them, and then updates the model and send the updated model to the learners. And this process is repeated till we learn enough. That means that our model has become good enough in making decisions. Now, the longer the process, that means the higher the number of iterations, the larger the delay, the higher the number of resources, computing, memory, network resources that we consume, but also the better the model learns. Now, let me just clarify why we are consuming network resources. As we said in federated learning, the learners and the coordinator exchange data. The learner send the model to the coordinator and vice versa. So clearly we have also a bandwidth consumption. Now, let me focus on an important aspect here, that is, who is going to participate in this learning process? Well, the answer is almost everyone, or better, everything. Indeed, there are concepts like micro ML or tiny ML that can allow tiny devices to perform a micro task in machine learning and contribute to the process with their own tiny resources and the data available therein. So while we can think of the coordinator as a node in the cellular infrastructure at the edge of the network, the learners can be devices that are scattered across the city. And here comes indeed the most interesting part of our story. And this opens new research opportunities. In particular, what scheme can we design to let nodes cooperate to learn better and more efficiently? So we know that, for example, in human teams, the result is often not the sum of the individual capabilities. Rather, it can be higher or lower, depending upon whether the team works well or not. So here we have something similar, and it is indeed up to us to make the most out of distributed learning paradigms. We need to create efficient, distributed, cooperative learning schemes. And these schemes should find the best trade-off between the ability of the model to make good decisions, the latency, and also the amount of resources, therefore energy, that are consumed. These schemes should also account for the fact that tiny devices can be easily powered through renewable energy sources, which will make the overall process much more energy efficient and sustainable. So, along with Sergio, we wish to thank you very much for your attention. And we hope that with your own help, if you are interested in joining this research activity, we can indeed devise innovative schemes that, without harming the quality of the decisions that we need to make, will make machine learning more sustainable.